So this graph here comes from Wikipedia, which, as I pointed out, is a fount of wisdom. And it gives a nice plot here showing you the chance of various things happening. Says that 68% of the time you will lie between the mean minus 1 sigma and mean plus 1 sigma. If you want to do 2 sigma, then you have an additional 13.6% either side. And if you go between 2 sigma and 3 sigma, that's 2.1%. So if it's either side, it's 4.2%. And then there's a pretty small probability of being 3 sigma, 0.1% either way. Note the one little subtlety, that sounds very small, but if we make 1,000 histogram bins, we have 0.1% either side, that's actually around two histogram bins will be 3 sigma away from their mean. So you need to worry a little in interpreting the significance of the results by asking how many histogram bins or how many results to actually look at. If you look at enough results, you'll always see interesting effects. So now we can ask whether this stuff possible errors in this type of analysis. And there are 2 types of errors, or at least 2 types of errors. These are 2 most important. There is sort of a mathematical error, namely the Gaussian distribution and the error being square root of n. That's an asymptotic result. It's not true in a sort of finite realistic case. It's just, but typically the errors here are small. Even for 25 as the mean result, we still got pretty reasonable answers. And so this mathematical corrections are not very big in most cases, and also not very important in the sense that they're easy to correct for. Because mathematics, you just there are many people, you just go to the statistics department and they'll correct it for you. Because that's well understood. Harder, which is what you need to use your wisdom to design your experiment, is biases. Namely, you need to be very certain that what you're doing is not got some hidden reason that it has a problem. And a good example here is if we were doing some sort of survey of people and maybe asking their political opinion again. We said, well, I'll save money by doing my survey in my local town, say that's Bloomington. Well, you would save money, and you can certainly, if you wanted to do your 1,500 people, which is what Gallup and Rasmussen typically do, you can get your 1,500 people in Bloomington. However, those 1,500 people would not be typical of the rest of the country. It's very unlikely to be. And so you will produce a biased answer. In fact, Bloomington's not even typical of Indiana. Bloomington, West Lafayette, Indianapolis, and Gary are pretty different from the rest of Indiana. So you will get biased answers if you're trying to predict Indiana and if you're trying to predict the nation by taking Bloomington. So in the case of physics, you'll get there's other forms of bias which correspond maybe to misunderstanding the experiment, so you measure things wrong, or you get backgrounds which you will misestimate, so you'll get incorrect estimates of things, and those are sort of model-dependent biases. So this is the hard part of these analyses. All these analyses have some underlying assumptions, and if those assumptions are wrong, the answers are not so good. This next set of slides, or which is the last set, correspond to showing that what happens when you do smaller plots with, smaller experiments. Here we, instead of doing 1 million people, instead of doing 10 million people, we do 100,000 people. So we take 250 events and we count them 400 times. And we'll get this rather raggedy looking graph here. Here's the appropriate normal distribution. Here's our histogram with 250s living somewhere around here. And it's pretty raggedy. Notice that the top is 10, the square root of 10 is 3. and we're roughly only, these results are not inconsistent with 10, and so you're just seeing the typical fluctuations you will get in any experiment of this size. Um, we can actually do another experiment like this by just rerunning the Python code. Python always gives you different answers by default. We'll discuss that in the next lecture. Um, and so it's again raggedy, but it's just raggedy in a different fashion. So you could say, well, this looks pretty messy, and actually, if you looked at that, and you would tend to say, well, we've chosen the wrong bin size for our histogram. We will choose a smaller bin size, sorry, a larger bin size. And here we've chosen a bin size not of 1, but of 5. And now we have around 50 events instead of 10 events. The error is still larger, 7. Square root of 50 is 7. By going to a larger bins, we've only got a factor of root 5 relative better in the error, but still it looks a lot smoother and is probably if you happen to do an experiment like this, you probably want to use this type of bin size and not the bin size you had at the previous case of 1. Really, that's so raggedy you couldn't really interpret it. So this points out something you need to do with this type of analysis. You need to think a little carefully about how to present the data. This is just the same thing done a second time, again with another seed. And actually this one looks a little prettier, but that's just life. It just happens this run was a little prettier. Runs are runs. Each run is an independent experiment. You will get different errors each time. So that's the end of that particular discussion. We will discuss this issue of actually Python having different random numbers each time in the next lecture.